Good morning, everybody. Good morning. Just going to let a few more people arrive. Amazing. Good morning. Fabulous. Okie dokie, well, good morning all, and welcome to another Spring Showcase. Today, I'm excited we're partnering with Anglian Water to find out how the Triple Carbon Reduction Project, in partnership with Oxymem, Cranfield University and Jacobs, aims to evidence a step change reduction in greenhouse gas emissions and electricity used in the wastewater treatment process. My name is Chloe Tooth, and I am the Knowledge and Communication Manager here at Spring Innovation. So for those of you that don't already know, we are the Innovation Centre of Excellence for the water sector, supported by all of the water companies across the UK and Ireland, as well as the supply chain and academia. We have the goal of enabling collaboration, removing duplication, and accelerating innovation across the water sector. So we are the custodians of the Water Innovation Strategy 2050. For anyone who hasn't seen that document, we're going to pop some links in the chat to that in a second. And this lives on our website. It's got 7 themes with challenges that sit under those themes that we want to be solving as a sector in there as well. So we also put out calls for innovation across those themes. So through our Spring Accelerator, the call for our Spring Accelerator 3 is around the theme of enhancing and protecting natural systems. So the call for this accelerator is live right now, but the application's closed today. So I'll make sure there's a link to further information for that in the chat as well. So today's service offering is about knowledge sharing. So we have 2 aspects to that. The first being our knowledge library on the Spring platform, where there's a bank of over 50 case studies for you to go and register and utilise and learn from on innovation projects from across the sector, with over 190 more case studies currently in the pipeline. So this is constantly being updated, so please do go over and register and check that out, as there'll be a link for that in the chat also. And just to let everybody know, the showcase recordings for most of those projects and today's project and any supporting documentation and links also sit alongside those case studies on our platform. So if you need to go back and revisit those, that's where they live. So this is a 2-hour knowledge showcase event, and we're happy to see there's 133 people registered for today's event, with representatives from Australia, United States and Finland, just to mention a few. So welcome to the call if you've managed to join us, and thank you so much for being here today. So today you're going to learn a little bit more about how the triple carbon approach represents a viable strategy to meet the net zero ambitions by implementing the solution at scale to reduce the marginal abatement cost of carbon emissions reduction. This showcase is number 19, and with over 2,700 people registered for these events, we're super happy and really proud of how these events are helping to disseminate knowledge from these innovation projects and accelerate learning across the sector. These showcases are all about being able to learn a little bit more about the project and take away those learnings and that knowledge and being able to embed those in your organisation. So that being said, we will be launching a poll at the end of this showcase to find out how interesting you found the information, and also whether you're planning to go or hoping to go away and use that afterwards. So please do submit your answers to the poll when that comes through at the end of this event. So on to today's session, I'm just going to run through the agenda quickly and introduce our speakers before I hand over to Mike Taylor to kick off this showcase. So obviously I'm going to introduce the speakers. Mike's going to take us through the importance of knowledge sharing. We're going to go through the project introduction and the journey to net zero. We're going to go into energy consumption and the hydrogen market and future opportunities. We're going to go into a really important part, which is the lessons learned within this project, go into a quick break, and then there'll be a Q&A session at the end. So please, if you do have any questions as we're going through, please pop those in the chat, and we'll do our best to answer all of those at the end of the session. If any of those questions aren't answered during that Q&A session, they will be uploaded alongside the case study on our platform as well. So I'll just go in to introduce the speakers before we go on to the next part of the session. So we've got Michael Taylor, Innovation Integration Manager at Anglian Water. We've got Julia Pizzagalli, Innovation Projects Manager at Anglian Water. We've got Barry Heffernan, Technical Director at Oxymem. We've got Connor O'Sullivan, Senior Consultant at ERM. We've got Luca Alibardi, Lecturer in Separation Processes at Cranfield University. and we've got Lisa Connor, Programme Manager at Jacobs. So without further ado, I'm just going to pass over to Mike and he'll take us into the next part of the session. Thank you.
Hi everyone. Yeah, I'm Michael Taylor and I work in the research and innovation team at Anglian Water. So you're all very welcome to the showcase event on our triple carbon reduction project. This is a project that I've been lucky enough to be involved in all the way from the early development stages, and I feel it's exactly the kind of project that the Offwood Innovation Fund is uniquely positioned to accelerate and support through development. It's very ambitious in the amount of different moving parts and that we can include in one single project, and this ambition is only possible when we can guarantee the dedicated time and the resources committed to the project over the whole duration. So from the offset, it was clear that there was a lot of potential for opportunities for this, but also a huge amount of uncertainty around the interactions between the water industry and the emerging green hydrogen market. As a sector, we have a lot to learn and a responsibility to proactively engage and embrace change as green hydrogen production ramps up. So that's why sharing our approach, our experiences and our learnings is really, really important on this project specifically. In this case, we're really lucky to have amazing project partners with the right attitude and learning mindset, as well as the processes provided by Spring that we've just been brought through to facilitate the standardization, the accessibility, and that long-term management of the project output. So we're looking forward to utilizing that throughout the project and post-project as well. This project still has a very long way to go before it's completed. We've got a program set out in front of us for that, but we believe that we need to share learnings and challenges all the way through the life of the project, as well as upon completion, in order to maximize that knowledge transfer opportunity. We hope that by sharing through events like this one today, that we'll help the whole sector to develop a better understanding of the opportunities presented to the water sector as enablers, as producers and as consumers of green hydrogen. If there's anything today that piques your interest or generates further thoughts, please engage with the project team today via the Q&A facility via Teams, or reach out to any of us individually in the future as well. Yeah, just wanted a really quick intro from me. I'll now hand over to Julia Pizzagalli, who will provide some further background and wider context for the project. Julia?
Good morning, everyone. So my name is Giulia Pizzagalli, and my role is Innovation Projects Manager in the Research and Innovation team at Anglian Water, and I am currently the Project Manager for the Triple Carbon Reduction Project, or TCR. So today I wanted to talk about the wider context surrounding the project and delving into our net zero ambitions, and explain how the Triple Carbon Reduction Project marries three fundamental goals for the industry in targeting reduction of process emissions and energy consumption, while also producing renewable energy in the form of green hydrogen via electrolysis. So as I'm sure you already know, the water sector pledged to achieve net zero operational emissions by 2030 and produced a route map via Water UK, identifying areas of interventions for innovation and pathways to achieve all these goals. So I just wanted to highlight a few of them, and you'll see how they're linked to the TCR project during the course of today's showcase. So the first intervention would be around low emission vehicles, so converting commercial fleet vehicles, so the tankers that we use, for example, to alternative fuels to reduce emissions and pollutions. The second area is around water and energy savings, both in clean water by adopting strategies to tackle leakage, adopting smarter and more efficient networks and catchments, but also in water recycling by developing strategies for optimization, investigation of new assets to target reduction of energy consumption from treatment. There is also a third area which is very important around process emissions, which are all the greenhouse gas emissions directly associated with our own treatment processes. And the intervention, so the goal would be to target reduction of up to 60% compared to the 2018 2019 baseline, and then carrying out a program of monitoring and baselining of these emissions, and then developing detailed pathways for reduction. The fourth area of interest would be around renewable power, so new solar, wind power coupled with energy efficiency measures to provide up to 80% of the sector demand without having to rely on grid generators, but also investigating new source of renewable power, so for example, green hydrogen. So process emissions are quite critical for the industry. When Anglian Water baselined for our own net zero strategy in 2030, they represented around 23% of the total emissions. And we estimated that when all the pathways that are highlighted in the roadmap will have been implemented by 2030, process emissions will still represent the largest fraction of emissions that we still have to tackle. So there's quite a lot of uncertainty still around how to measure and how to reduce process emissions. And the roadmap itself acknowledges a little bit of a lack of coherent strategy for reduction of process emissions at scale, apart from offsetting. In wastewater treatment, one of the prevalent greenhouse gas emitted is nitrous oxide, which has a global warming potential of almost 300 times greater than CO2, and is mostly produced during biological treatment for ammonia removal. So no one factor really causes nitrous oxide emissions. As you see there, it could be low DO, ammonia peaks in nitrification. It could be a low COD to N ratio in denitrification. It's really a complex combination of parameters. And also the magnitude of emissions strongly depends on the operating conditions in which we operate the treatment processes that we run. So there's no silver bullet for reducing nitrous oxide yet, hopefully, but we have developed a hierarchy of interventions from the easiest to the most complex for implementation. So the first step would be around operational optimization, so trying to achieve a balance between process emissions reductions and energy efficiency drivers and operational carbon from electricity. So these would be quite marginal but easier gains in the route to process emissions elimination. Then we've got process modification and enhancement, so we can modify our processes. So for example, by trying to remove total nitrogen instead of ammonia, by adopting new technologies for treatment, such as membrane aerated biofilm reactor, MABR. But all these interventions will have a significant capital cost and carbon. So we'll have to try and maximize the opportunities from other investment drivers. So one of them could be around nutrient neutrality, but also we'll have to try and explore the co-benefits to offset the cost of this investment. Then the third step would be asset replacement. So this is obviously quite unlikely to be realistic at large scale, at least until the end of life of the current asset base. And then the fourth step would be to cover our asset and then collect the off gas and treat it. But obviously this is quite costly and quite operationally challenging. So Barry will go into more detail later on in the showcase, but one of the technologies that has been identified with a good potential to replace or enhance conventional biological treatment is MABR, so membrane aerated biofilm reactor. In general, MABR inherently reduces relative energy demand compared to conventional treatment, so bubble treatment like activated sludge, by supplying air at a lower pressure and with a much improved oxygen transfer efficiency. It is possible to mix oxygen with the supply air into the MABR, and we do think that by doing so, the oxygen transfer efficiency could be increased even more. MABR also has a significant potential for nitrous oxide emissions reduction and capture at point source, so in the off gas of the membrane, making it again a point source emission rather than a surface emissions like activated sludge. However, we do know that the widespread adoption of MABR or these new technologies could be costly and quite challenging, and unlikely to occur at large scale until the end of useful asset life of our base. So the triple carbon reduction project aims to integrate MABR and green hydrogen generation via electrolysis, demonstrating an operational solutions that could help accelerate the deployment of MABR and also reduce the abatement costs of process emissions reduction by exploring the co-benefits of hydrogen generation via electrolysis. So the project aims to achieve three main carbon benefits in line with the Net Zero Roadmap 2030 and those areas of intervention for innovations that we've seen earlier. And so three reductions, hence the name triple carbon reduction. So the first aim would be elimination by demonstrating a viable alternative wastewater treatment process, the MABR, targeting elimination of nitrous oxide emissions from secondary treatment. The second aim would be reduction by achieving up to 85% reduction in energy consumption compared to conventional treatment processes that we currently use. So we've baselined, again, the activated sludge process. And the third aim would be generation of both oxygen via electrolysis that we can use into the MABR, but obviously also generation of hydrogen for using applications that are currently quite difficult to decarbonize in our sector. And obviously the scope of this decarbonization depends on the scale of hydrogen that we'll be able to generate. So to add to the circularity of the system, we also have a view at looking at hydrogen production using treated effluent from wastewater treatment to recover resources and avoid compromising the drinking water and the resilience that we are building to face climate change in the future. So at the core of the project, we have a small demonstration plant that is currently being deployed at Cambridge Water Recycling Centre. So it all starts with an electrolyzer. As we know, an electrolyzer uses renewable energy, in this case, CHP generated electricity to split water into its molecular components, oxygen and hydrogen. So we are producing around 90 kilos of hydrogen per day and 730 kilos of oxygen and using potable water in this case because the pilot plant is quite small and we have site constraints, but obviously, as I said before, looking into treated wastewater as a feedstock is part of the project still. So the oxygen will be then fed into a secondary MABR, which will be in a full biofilm configuration and takes a side stream of settled sewage. So the MABR is already up and running on site, has been for a few months, and we've started to run it and currently trying to gradually increase flow to treatment. And then the plan for the next few weeks and months will be to try and test different enrichment percentages in the supply air until we ideally go to pure oxygen if we can. So we will be monitoring nitrous oxide production, both in the salt phase and gas phase, so that we can understand the nitrous oxide production and at the same time determine the optimal operating conditions to try and achieve a balance between our three drivers, so energy efficiency, emissions reduction, and effluent quality, of course. The hydrogen, so this was for the oxygen. The hydrogen that we produce in the electrolyzer will be compressed at 300 bar and then stored primarily in a hydrogen tube trailer, as you can see the photo there on the bottom left. So we partnered with an off-taker in a region, Element 2, who will be taking the hydrogen off-site and will be testing it in a hydrogen vehicle testing facility. So this partnership will allow the project to gain a bit of a deeper understanding around the hydrogen markets that are available in our region, what the demand is looking like, what incentives we could get with this hydrogen quality, and hopefully will provide us good case studies to support the decarbonization through the use of hydrogen. So as I said before, in terms of timings for the project, the MABR is already on site. It's been up and running and being optimized. We are expecting the second bit, the electrolyzer, to arrive in the next couple of months for ideally a forecasted start in June for a 6 months trial. So that takes us up to December when the project ends, and we will have all the simulation activities of hopefully very good results. So the triple carbon reduction project is not just the demonstration plant. On top of the 3 main outcomes around generation, elimination, efficiency that we can achieve through the demonstration plant, we also aim to explore involvement, engagement from local communities, customer perception around the project itself, but also around energy futures, sustainability and climate change initiatives from water companies. And we've been carrying out this work package with the University of East Anglia. A longer term, and through our partner ERM, we aim to include growth and scaling of this solution to produce a business case and lay out a legacy plan for this solution to be implemented at scale in different contexts and different geographies, maybe with different sources of renewable energy. We also aim to demonstrate the sustainability of the integrated system through a life cycle assessment and its potential for this solution in aiding the decarbonization of the water sector. So the LCA is through a work package with a working group out of Imperial College London, whereas Cranfield University will be looking at identifying alternative approaches for cost-efficient and more sustainable pretreatment of final effluent. So through triple carbon, again, we aim to deliver significant benefits, obviously, to the water sector. And we want to explore cross-sector collaboration and liaise with the energy sectors and players active in the hydrogen area that we may not have been in touch with before. So first of all, again, we are aiming to prove that the triple carbon approach is a viable approach to meet the industry net zero ambitions by implementing this solution at scale to try and reduce the marginal abatement cost of emissions reduction. We also want to demonstrate the viability of co-locating hydrogen generation in wastewater treatment facilities and define a best practice for the process scale up for the whole sector. Another benefit of the project is around resource recovery, so both in terms of the oxygen that we can use into the MABR without being wasted, but also in terms of the treated wastewater, like using treated wastewater as a feedstock for electrolysis. So treated wastewater final effluent doesn't compete with other water uses. Its availability is less vulnerable to the effects of weather and climate change. And also it's conveniently produced in wastewater treatment centers, where we also have a use for the oxygen. And this obviously makes the case for co-location even stronger. So this was just a really basic overview of the project. There are so many different moving parts, but we will go into a little bit more detail on some of them with the next speaker. So this is it for me, and I'll just pass the torch to Barry for a deep dive into MABR.
Great. Yes, so thank you all for being here today, and I'm going to give a brief introduction to Oxymem's MABR, the MABR in general, and also how we think the MABR can be really useful for reducing carbon emissions from wastewater treatment plants. The MABR itself stands for a membrane aerated biofilm reactor. Its key advantages is biological process intensification. So you can drop our modules into existing wastewater treatment plants. That allows you to increase your capacity of your plant with essentially zero footprint and increase that you're installing in the existing tanks. It also has some advantages in energy use versus conventional systems. I'll go into a little bit more details on what those advantages are later on. It's also the fastest and least disruptive upgrade you can do, because you're dropping into existing tanks without taking them offline. So the technology itself, the Oxymem MABR, we manufacture our membranes from silicone, so they're a dense porous membrane. it's important to say again, we're transferring oxygen across the membrane to a biofilm growing on the membrane. So you can see the image here on the lower left-hand corner showing that biofilm growing. We have no pores that can clog like conventional ultrafiltration membranes. So we're not worrying about cleaning the membranes with chemicals which can reduce their lifetime. Instead, the biofilm is our friend, and we actually need the biofilm to grow. That's what's going to remove the pollutants from for us. Our modules in particular, they're housed in stainless steel frames, and the headers are made from PVC plastic. I see there was a question earlier on about the carbon footprint. We'll have to go into that in more detail on one-on-one, but in general, we've looked at the payback time in terms of if you were to change out fine bubble diffusers for our module. And in the UK, it would take roughly about 4 years before the embedded carbon in the MABR module would be offset by the savings on electricity use alone. That doesn't consider any savings from nitrous oxide reductions, which is a slightly different matter. So just purely on the savings from using less electricity. In terms of how the MABR works, we have our module inside which all of the membranes are housed, and then we have about 600, 700,000 individual fibers. These fibers are fed then with typically air from the top to the bottom, and the oxygen then transfers out across the dense membrane into a biofilm which is growing on the surface. So the fiber itself has two functions. It acts as support for the biofilm to grow, and then has a means of transferring oxygen into the liquid. As I said, we typically use air. That's just because blowers are really plentiful. They're cheaper. It is possible to use pure oxygen. We've only ever done one trial with that previously as Oxymem, and that was 7 years ago, 7, 8 years ago. So this project is all focused on, can we use that pure oxygen, and can we resolve some of the uncertainties around the benefits or the negatives of using pure oxygen. I have a couple of slides later on which I'll show it. In terms of energy use, might deal with that here. So one of the key advantages of the MABR is that we're operating at low pressure. So typically we install the modules on the top surface of a tank, and they're about 2 meters deep. So we need about 300 to 400 millibars of pressure to make sure the MABR operates really well. That's considerably less than for activated sludge systems today. Most activated sludge plants that are built today, the new ones, they're at least 7 meters deep, often 8, 9 meters deep. So they need considerable more pressure. But the real saving for the MABR is that we can transfer oxygen directly to the bacteria. So we're not trying to get oxygen into a bubble and then get the oxygen out of that bubble into a dirty water. And when you have clean water, you can get one oxygen transfer efficiency. When you have dirty water, you get another worse one. So because we're transferring the oxygen directly into the biofilm, we operate with about half of the airflow requirements compared to fine bubble diffusers. So compared to a brand new plant, we have roughly half the pressure, half the flow rate. So we just need a lot less energy to transfer the oxygen compared to conventional systems. So that's one advantage in one area. We can reduce carbon emissions. I guess I would say when we started off with MABR in the first place, it was almost 10 years ago, more than 10 years ago at this stage. A lot of countries, including the UK, Ireland, they have embraced clean energy, maybe not as much as we'd like, but a lot more than they used to. So what you can really see is that the emissions factor for the grid is going down and down. So while the MABR might be able to reduce your energy use, which will save you some money, in the long run, probably having a really efficient aeration system won't impact on your carbon footprint that much, because the electricity makeup of the grid will be so clean that it won't have so much of an impact. So maybe that will come back on to where to use an MABR and how we think we can have an impact on process emissions. This is just a quick slide. Sometimes we use pure biofilm systems where the MABR does all of the work. That's the system I'm showing on the right-hand side. Most of our applications today are IFAS applications where we're dropping into existing infrastructure to give them a boost. For the purpose of this project, we focused on a pure biofilm system. I guess that the main point, if you have an IFAS type application, the MABR is typically removing 20, 30, 40% of the ammonia. That means you're limited on the overall process efficiencies and savings you can get, because you're still going to rely on fine bubble diffusers for removing most of your COD, most of your ammonia. So if you have a pure biofilm system, then the MABR is doing everything. It's removing the COD, it's removing the ammonia, then you can get the maximum benefits from the MABR, the most energy savings, and perhaps, hopefully, maybe the most nitrous oxide reductions as well. So sorry, just 1 second. So why to use the MABR? So the first one is really land intensification. So this is a picture of a site in southern southern England. As you can see, it's hemmed in on all sides. It's got a road on the left-hand side. It's got a golf course on the right-hand side. If this plant needed to be upgraded, a conventional approach would be to build new tanks. But what are you going to do? Where are you going to build it? There's no space left on that site. So maybe you're going to have to go over there onto that golf course, and the chances of that are maybe pretty slim, or maybe to none. The alternative, of course, is to, in our case, is to install MABR modules in the existing zones, in the anoxic tanks. And this is a plant where an MABR will ultimately be installed. In terms of carbon emissions, there's some real obvious advantages here. So instead of having to pour new concrete, which has high carbon emissions, you can just install the modules in the existing infrastructures. So there's an obvious saving on carbon emissions there straight away. Plus, of course, it solves a bigger problem for the plant in that they can increase their capacity without having to go knocking on the door of the golf course and try to get that land off them. In terms of energy efficiency, this is just a quick slide. This is a project we have in Canada. There's 8 MABR modules installed. They're treating about 20% of the ammonia, I guess in less than 5% of the overall volume. I need to calculate it, but you can see how small the MABR modules are here. The other thing you can see is that the fine bubble diffusers are working away on the left-hand side. And all those bubbles are wasted energy. In comparison, the MABR modules are just installed, and you can't see any aeration at all because we're essentially bubbleless aeration. So I kind of just use this slide to demonstrate how the MABR can be more energy efficient. Again, I mean, obviously in this plant we save carbon emissions for not having to build new tanks. In terms of nitrous oxide emissions, this one is more interesting. So we're obviously transferring oxygen from the aluminum across into the biofilm. At the same time, ammonia is coming from the bulk liquid. And assuming we don't have any carbon coming in, what happens then is the ammonia gets into the inner layers of the biofilm, and the MABR basically produces nitrate. And the nitrate then has to diffuse back out towards the bulk liquid, because it can't transfer through the membrane. And because there's nitrate produced, there's also the potential that we can produce nitrous oxide. Nitrous oxide is, of course, a gas, so it can go in both directions. It can also go back into the membrane, and it can also diffuse out towards the bulk liquid. But the interesting thing about the MABR is what we're showing here. It's a counter-diffusional biofilm system. So we can get simultaneous nitrification, denitrification. If we control the oxygen flow versus the feed supply, what can happen is then that the COD, something like acetate, can diffuse rapidly into the biofilm, where it will come in contact with the nitrate and the nitrous oxide and converts them to N2 gas. And that can prevent the emissions of nitrous oxide. Of course, there's still the potential that the nitrous oxide that's produced in the MABR module can transfer across through the membrane. And if that happens, though, I mean, it's an opportunity, I would see it, that you've got relatively high concentrations of nitrous oxide that you consider utilizing or recovering. Certainly it will be much easier to recover the nitrous oxide from that point coming out of the off gas from the MABR versus trying to cover entire activated sludge plants to try and capture that nitrous oxide. In terms of whether, I know there was some questions earlier on, can MABRs reduce nitrous oxide emissions? I think yes, no, maybe might be the answer. So if it's greenfield sites, yes, I think if we design MABR plants well, we can reduce nitrous oxide emissions. If you have an existing plant and you want to drop MABR modules into that plant to help reduce the nitrous oxide emissions, then it's much more of a case of yes, no, maybe. And the reason for that is it'll really depend and how the existing plant is configured and how it's operated. I think plants that are operating with only aeration and the nitrification is on the edge, they can benefit enormously by having MABR plants. Well-operated plants that have anoxic tanks, they may not need an MABR, they may have low nitrous oxide emissions. So it'll be a case-by-case basis, and there will need to be more studies such as this one to confirm all of the advantages of the MABR. When it comes to why we're going to use pure oxygen, I think this slide is a little bit interesting. So if we use pure oxygen versus air, one of the things we can potentially do is end up transferring more oxygen. So there's a risk that the biofilm will become completely aerobic, and the anoxic layer I'm showing here won't exist, which could mean that we end up producing more nitrous oxide. Not sure if that will happen. Alternatively, we might be able to keep the biofilm layer thinner and get higher nitrification rates, or at least achieve lower bulk ammonia concentrations because we have a more aerobic biofilm. All of these things will hopefully come out in the wash as we go through this study. So this one, the last thing to show the advantages is how to deploy an MABR. And this is just a quick video, about 30 seconds, to show how a plant can be updated in less than 2 hours once you have everything ready. So I think Emily is going to play this, or I'm not sure, do I need to press a button? Because just leave it to it. So. So that was just a quick video to show how an MABR can upgrade a plant rapidly. I'll go on to the next slide so it doesn't keep playing itself. One thing I would say is, I mean, there are alternative technologies that can be used to upgrade existing plants, such as MBBRs. But as you saw from that plant there, it's a plug flow type plant. It's long and narrow. You couldn't just drop MBBR carriers in there. You'd have to take the plant offline and do a lot of civil works to try upgrade it. Whereas with the MABR, the MABR modules were installed while there was still flow going to all of the lanes, and the plant continued to operate. In terms of the triple carbon reduction project that we're working on, a couple more slides and then I'll finish up. So we want to see, can pure oxygen make the difference? What difference will have versus air? So we've built this small-ish, largest demonstration plant. We've built 2 tanks side by side. Each tank will have 3 MABR modules. We've started them both up already. Initially, we were feeding both of them with air. And as once we were happy that basically we've got the max performance out of both of them and good performance, then we're going to switch over to pure oxygen for one of the lanes. And then we're going to see what difference it makes to the performance of the system, the one running with air versus the one working with pure oxygen. All of the time, of course, monitoring our nitrous oxide emissions as well from both lanes to see if there's any difference between the plant that has pure oxygen versus the plant that's only operating with air. And then just the plant is built already. So just a couple of pictures of it. You can see here we have some banks of oxygen cylinders here as well for the situations where the electrolyzer isn't available. And then one last slide before I'm finished. So we have started it up, and just showing this chart here, where it's always good to show some slides. So we've been gradually increasing the loading rate to the MABR. So we've got up to about 1 gram of N per meter squared in a day. And then I'm also showing the ammonia concentration. So for long periods of time, we had very low ammonia, less than 1 milligram per liter. Recently, it started to increase a little bit, up to about 2 milligrams per liter. We're not getting simultaneous nitrification, denitrification right now, but interestingly, we don't have any nitrous oxide emissions in the liquid, but we do have a lot of nitrous oxide in the off gas. So we're just at the very early stages of gathering the data. So hopefully in about 6 months' time, we'll have a lot more information to report back and see can the MABR really help reduce nitrous oxide emissions and also other carbon emissions. So that's it for me. Thank you very much.
Okay, thanks, Barry, and yeah, good morning, everyone. So I'm going to be talking about, I guess, the hydrogen market and I guess the wider context on the economy and the links with water as well. So I think, firstly, I guess hydrogen is being considered in the UK as one of the, I guess, levers that can help decarbonise a wide range of sectors. So existing hydrogen demand is primarily focused on industry, and then this is looking to grow in the future, but then hydrogen could potentially also be used to decarbonise other sectors, whether that be power, heat, or transport as well. Whilst there's the figure on the right kind of shows the, I guess, very wide range of uncertainty, it does show, I guess, a very significant increase in the potential hydrogen demand that we could deploy in the UK. I think one of the questions, well, the key things is that while there's been a big focus on decarbonising and reducing CO2 emissions, I think water has often been considered as a bit of an afterthought sometimes. So sometimes where the water is going to be abstracted from, or the source of the water, can be a constraint to many low carbon projects moving forward, and this is often very regionally or a local constraint, depending on where the projects are located. But I think in the UK, there are a couple of key drivers of reducing the available water supply. So these are primarily climate change, existing over extraction, and population growth as well. So whilst hydrogen is likely to play a fairly significant role in helping the UK decarbonise and across various sectors in the economy, where we source the water from is likely to be an increasingly important question that needs to be considered as well. So if we are to take an example and look at Anglian Water in the UK, the map here on the right is showing Anglian Water's water resource management plan and their supply and demand balance for 2045. So what you can see here is that I guess the regions in red are where water is likely to be a significant constraint. So these would be particularly catchment areas where water stress is likely to be significant, which is, well, covering most of the region by 2045. So where I guess we can think of climate change as very much a global challenge, water stress and the water balance in a region is very much a local issue. In Anglian Water, the region that Anglian Water services faces a number of particular challenges. I guess it's one of the driest regions in the UK, and this is only predicted to become drier in the future as the effects of climate change increase. But it also has one of the highest population growth outside of London. So this puts an increasing stress on, I guess, the water demand going forward. So where, I guess, the public water companies, they have a legal obligation to supply domestic water demand to houses for, I guess, washing, cleaning, cooking, drinking, as well as fire services. In terms of industrial decarbonisation, there is, I guess, currently no legal obligation for the public water companies to supply non-domestic demand. So historically, where the public water companies have been able to meet these demands, in the future, as they have no obligation, this could be a very significant constraint for low carbon projects, including those for hydrogen production moving forward. These hydrogen projects may have to come up with alternative water sourcing strategies than looking at the public water companies, as and there's unlikely to be the opportunity to directly abstract either from groundwater or surface water as well. So where the water comes from is likely to be a significant challenge for permitting projects moving forward. In terms of hydrogen production technologies, the water intensity is very dependent on the technology type. So you can see here on this figure showing a range of different hydrogen production technologies, both from, I guess, the typical, the blue hydrogen production technologies, which consider carbon capture and storage as well as the electrolysis-based ones, which you can see the bottom two on the figure. This does show that the electrolysis-based technologies are likely to be more water efficient than some of the ones that include carbon capture technologies. This is likely to be, well, it's primarily due to the fact that the cooling requirement of carbon capture technologies is likely to be more significant. So reducing the cooling demand of your hydrogen production technology is a very, well, it can significantly improve the water efficiency of the hydrogen production moving forward. So by increasing the efficiency of your project, you can reduce your cooling demand and therefore reduce the water intensity moving forward. So in some regions, project developers are already considering trying to reduce the water intensity of their hydrogen production by deploying air cooling as well. So this is something that is well, needs to be considered going forward when selecting which technology would be most suitable for a hydrogen production project. In terms of hydrogen production, this is for both electrolytic-based hydrogen production and for, well, blue hydrogen production technologies, but you typically need a very ultra-pure water for your feedstock to make hydrogen. And to make this, you typically will have a processing plant. So to make this ultra pure or demineralized water. But the amount of input water that is required to make this ultra pure water will very much depend on its quality. So what this figure is trying to show is that if you were to take 1.4 meters cubed of groundwater, that would only produce 1 meter cubed of ultra pure demineralized water. And the lower the quality of this water, so if you're taking seawater as, I guess, your lowest quality or water with the most impurities, that can be over 3 meters cubed of water that is required to be processed to make just the 1 meter cubed of water. Where there's now, well, an opportunity to, I guess, reduce the reliance on the environment or the public water companies is to then use wastewater streams, which I guess this middle stream, and the range of water input that is required to make this ultra pure water for hydrogen will vary significantly depending on the quality of the wastewater stream. But this is something that I think could be explored in much more detail for industrial sites and the opportunities for co-location with electrolysis projects. And those of existing industrials moving forward. So what opportunities there could be to utilize wastewater streams to make hydrogen moving forward for decarbonisation projects is something that could be very interesting in the future. On this slide, I just wanted to highlight where some of the water is going in the electrolytic hydrogen production process. So where electrolysis, the stoichiometric limit will typically be 9 meters cubed per ton of hydrogen. When you're actually looking at deploying this in a project, you'll typically be requiring that demineralized feed, which is about 10 meters cubed. But before that, you'll have either, depending if you've got a raw water, a wastewater, or even a seawater feed, the actual source of water that goes into making your hydrogen will be significantly higher. And this is where, as well, once you've added cooling on top, the volumes of water that could be required could be very significant. So well in excess of 30 meters cubed per ton of hydrogen in some cases. So essentially, as the water quality decreases, the more input you're required at the start to make your pure water for your hydrogen feedstock, but then the cooling water on top of that needs to be considered as well. And then that figure on the right hopefully just shows you, I guess, some of the flows for where the water is required as well. I think, well, finally as well, just to, I guess, consider the energy requirement of processing water. So what you can see here is the three small squares on the left showing you, I guess, the energy requirements for processing up to 1 meters cubes of water for electrolysis. But if you're then comparing this for the energy requirement of the electrolyzer, it's significantly dwarfed, as you can see by the big square on the right. So although water can very much be a constraint in the local region for your hydrogen production project, you'll obviously need a sustainable source of water to ensure that your hydrogen production project is viable. The energy demand of the electrolyzer is the thing that is most significant in terms of the cost viability of the project, and this is why when you're looking at future opportunities or announcements for hydrogen projects, they're typically located next to large supplies of renewable energy, as this is what is going to be the most significant factor in ensuring that you can bring your cost of hydrogen down. So in terms of the energy demand, the processing of water is it's very insignificant in comparison to that of the electrolyzer. So although it is quite an energy intensive process on its own compared to that of electrolysis, it's very small, and it is likely, in terms of cost, it's roughly, you see, figures quoted around 1% of the life cycle cost of making hydrogen, which can typically rate, there's one source suggesting between 2 to 5 cents per kilogram of hydrogen. So just to summarize, I guess, is that whilst water could be, water could be a constraint for hydrogen projects moving forward, there are definitely opportunities in the future to for hydrogen projects that are looking to utilize wastewater, and the energy consumption of the electrolysis is likely to be significantly more important in terms of the economic viability of the project moving forward. And that was my final slide. Thanks for listening. Happy to take any questions at the end.
And I think it's on me now. Hello, everyone. My name is Luca Libardi. I'm a lecturer at the Cranfield Water Science Institute. And I wanted to present some of the aspects that we are exploring for the triple carbon reduction process project through Cranfield, and my presentation will mainly be around the water quality requirements for electrolysis, and then look at the opportunities and synergies that those strict requirements might open for the water sector. So, quick outline of the presentation. I'll briefly introduce the types of electrolyzers that are available in the market. We're trying to focus on their water quality requirements, and then trying to link those with the characteristics, the typical characteristic of final effluent, what we know and what we don't know yet. And then, provide a bit of an overview of the role of electrolysis and synergies and opportunities that locating an electrolyzer in a wastewater treatment plant can offer. So if we start from water electrolysis, there are mainly two technologies developed at commercial scale for low temperature electrolysis. The first one is alkaline water electrolysis, AWE. This is a technology that has been developed over the last 50, 60 years. So is probably the most mature technology and among the cheapest electrolyzer available in the market. Here you can see a typical configuration of a AWE electrolyzer, and just want to flag the left-hand side of the slide represent water treatment steps before the water is fed to the electrolyzer. So typically there's a pre-treatment step followed by a reverse osmosis treatment and a deionization step before this high purity water is mixed with potassium hydroxide or sodium hydroxide to make the electrolyte that for AWE is liquid, is this mixture of high alkaline potassium hydroxide or sodium hydroxide, around 30% in weight, that is fed into the electrolyzer. So there's a requirement of deionized water for the makeup of the electrolyte. I've mentioned the main advantages of AWE. The disadvantages are that it's not the preferred, probably not the preferred solution to be combined with renewable power, because it struggles to ramp up and down so quickly, it also has a slightly larger footprint compared to other technologies. But of course, there's a clear advantage of the maturity and the level of application of this technology. The other option is proton exchange membrane electrolysis, or PEM, PEM. Again, so newer compared to AWE, probably developed over the last 20 to 30 years. The key advantage here is that the electrolyte is a solid, is a polymeric material, so we don't have to deal with the high alkaline solution as for AWE, but we still need, of course, requirement, if not of high purity water. Again, if we look at the left-hand side of the slide, we see basically the same treatment steps, RO and deionization, but here the requirements are even higher in terms of quality compared to AWE. So very low conductivity or high resistivity water, that we refer to it as ultra pure water. The main advantages of PEM is a more compact unit, so a smaller footprint compared to AWE, and it also have an ability to ramp up and down quite quickly. So it's probably the preferred electrolyzer to be combined with renewable power, because it can follow better that fluctuation of power from wind or solar. Disadvantages or cons is that it's relatively more expensive, mainly because of the need of expensive polymeric membranes, and also some noble metals like iridium and platinum as catalysts for the electrolyzer. So if we look at the quality that these units of the water requires, again, these are just some data that we collected from the web. So typically we can say that alkaline water electrolysis requires type 2 water, if we refer to it as using the ASTM standard. But it can of course start from potable water with a further treatment before it's fed to the electrolyzer. And typically, as I showed before, the steps are reverse osmosis and deionization. PEM requires a slightly higher quality, so refers to type 1 ASTM standard water, again, so is ultra pure water. So what does it mean, type 1 and type 2 water, looking at ASTM standard? So those are the characteristics, the requirements. So if we look at conductivity, so type 1 is the purest type of water. We are at 0.05 millisiemens per centimeter in terms of conductivity. Type 2, we are slightly higher, around 1. Total organic carbon content, maximum allowed 50 micrograms per liter, not milligram, micrograms per liter. And again, you see some characteristics in terms of sodium, chlorides, and total silica. So how does it compare those characteristics to typical water sources that we might consider for water? So if we look at seawater and we use conductivity as a term of comparison, so typically seawater, we are at 55,000 millisiemens per centimeter, and we need to go down to 0.05. So there's 5-6 order of magnitude of reduction. If we start for final effluent, we start to get some advantages. It's a cleaner type of water, and of course, with much less conductivity and a concentration of dissolved material and compounds. So we are around 500 to 4,000 millisiemens per centimeter. So we start to see some advantages of considering final effluent compared to seawater for electrolysis. Again, reverse osmosis. So the osmotic pressure in reverse osmosis is directly proportional to the concentration of compounds that you want to remove. So of course, if we start for a much lower conductivity value, we have a clear advantage in the energy cost to produce that high purity water. So we start to see the advantages of looking at final effluent from wastewater treatment plants. So now, wastewater treatment plants, how do they look in terms of characterization? So of course, we got plenty of data in terms of concentration of organics, COD and BOD, nutrients, some values for iron if there is a consent, and so on. Because it's typically what the industry measure to meet the consent. But of course, we might lack some knowledge in some parameters that are essential to understand how far final effluent is from the requirement of an electrolyzer, in particular conductivity. We might not have much data about silica and sodium. We might have some data about chlorides and dissolved organic carbon. And so through triple carbon reduction process, we're trying to feed that gap and develop some knowledge on how to approach the treatment of final effluent to meet the requirement of electrolyzers. So we're looking at an advanced characterization of final effluent. So some preliminary data that we've done looking at 3 treatment plants, a very small 2,000 PE plant and 2 larger 200,000 and 300,000 PE plants, just as a sort of initial type of plants we could target. So if we look at conductivity, the bars on the left, so value the ranges between 500 and 1,000 millisiemens per centimeter, and again the requirement is 0.5 for the electrolyzer. So if we look at dissolved carbon, again, a final effluent in terms of dissolved carbon, we are around 10 milligrams per liter, and the requirement is to go down 0.05 milligrams per liter. And an important aspect that we started to notice is that about 25% of that dissolved carbon is low molecular weight neutral organic compounds and urea that are the trickiest part of the dissolved carbon to remove through membrane technologies. So there's a good chunk of material that we might struggle to remove using membranes. And then some numbers related to sodium and silica. So in some cases, we're already below, if we look at sodium, the requirement, sometimes not. That's the variability nature of the variability of the effluent. And then we started to do some preliminary tests using ultrafiltration and reverse osmosis in 2 passes with the plant of 200,000 PE, and we wanted to see how low we can go with this sort of traditional approach for water purification. So again, you see in this graph the 4 steps from the initial characterization to the final quality after 2 passes. So if we look at conductivity, the yellow bars, and this is a logarithmic scale graph. So we can go down to 100 millisiemens per centimeter with UF and 2 passes RO. And again, the next step would be to go down to 0.05. It is a good result because typically you have an ion exchange process downstream of the UF and RO that will clear that final value of conductivity. Again, close for silicon and sodium. and still a bit of a way to go for a dissolved carbon. So minimum value around below 1 milligrams per liter. But again, the requirement is to go 0.05. And then we again look at the more detailed characterization of that dissolved carbon. And again, is another logarithmic scale. So don't be confused of the sizes. Look at the numbers. So if we look at the quality of that dissolved carbon, 73% is still that fraction made of low molecular weight, neutral compounds that is very difficult to remove. So that is something that we need to tackle, and we need to try and understand how to approach it. Just to finish off, I wanted to kind of summarize some advantages and synergies of locating an electrolyzer in a wastewater treatment plant. So this is a case for 100,000 PE with a 1 megawatt electrolyzer. So we look at using final effluent. So how much final effluent will the electrolyzer need? It's probably below 0.5% of the dry weather flow of the plant. So it's a minimal consumption of water. So little impact on the natural environment from taking water from the final effluent. If we scale up the electrolyzer to 5 megawatt, it's probably around 0.2%. So it's not a large amount of water. Of course, the electrolyzer will produce hydrogen. The water industry might consider using that hydrogen for fleets, or to substitute diesel, for example, for backup power. That's a solution that is developed in the market and is being used. But it can also consider other uses. So government allow 20% of blend of hydrogen into the national grid. Can that be an opportunity? Or what are the other uptakers for hydrogen? Chemical industry, steel, refinery, glass, bricks. So high energy, high heat industry might want that hydrogen to replace natural gas. Of course, the electrolyzer will need power. Preferably, you want to use renewable energy to reduce the carbon footprint and the carbon intensity of the hydrogen. So that's an estimation. We have 0.5 kilograms of CO2 per kilogram of hydrogen. That's pretty low compared to the 2.4 that is the threshold that the UK government consider for low carbon hydrogen. But there's also an opportunity for example, grid balancing services to switch on the electrolyzer when the grid might need help in balancing the demand, and then they can get some reward for doing that. Of course, the electrolyzer will produce oxygen. That there's a clear internal consumption. So again, we estimated that a third of that demand can be met from the electrolyzer. But if you use a much more efficient technologies like the one Oxymem is supplying, probably you can meet a higher demand. Or you can also consider other uses in industry of that oxygen if there is an excess. Heat can be produced from the electrolyzer, it can be used, but also we're looking at water pre-treatment. So the electrolyzer requires high standards in terms of purity, but we can set up a plant for treatment that final effluent to meet the demand of the electrolyzer, but also other demands from industry, from agriculture, or from potable. So is understanding, of course, here is the synergy of and the opportunity that electrolysis can offer to the water sector. So considering that it can produce water to meet the demand from the hydrogen economy, but at the same time producing water for other uses, because the type of treatment flow sheets that are needed for the hydrogen economy are very similar to those that are considered for water reuse. And that's all I wanted to say. Hopefully there's enough for a good discussion. Thank you.
Hello. Hi, thank you. Thanks, Luca, for that. I think it's over to myself now to just run you through some of the project insights or the lessons learned that we've achieved over the last 2 years while trying to deliver the project and all the objectives that our colleagues have explained to you over the course of this presentation. So let me just just give you a little bit of a recap there. It's an Ofwat Challenge Breakthrough project, and it's about 4.7 million was the contract award. We launched officially in about May 22, and as Julia highlighted earlier, we're aiming to complete towards the end of the year, December 24. We've got 12 partners, and that includes 5 water companies and 2 suppliers as well. So it's a large team delivering all the objectives that we've pointed out to you today. And I think it's key just to note, as all the colleagues have pointed out, it's not just a pilot trial of an MABR and the electrolyser system. It's actually generating the learnings from that trial, disseminating it out to all of those interested in these pathways. But it also includes hydrogen end-way pathways, understanding public engagement for technology such as hydrogen. We've got carbon life cycle assessment, so we can understand the implementation of the pathways in the water sector itself. And all of this at the end of the trial in December, we will be able to get the results and disseminate that to the wider audience so we can share the learnings. So I'm just going to run through with you now. I'll skip over that one. Really, I think our key project risks and how we've mitigated it is a good record, if you like, of what we've learned so far along the way. And I'm going to start with one of the key ones, which is the procurement. So we knew when we tendered the project that the electrolyser of our scale needed may not be available. With the hydrogen market catching up and the high demand for hydrogen at the moment, an electrolyser of scale for our pilot trial may not have been readily available. We did initially think that we'd go for a PEM electrolyser and ended up with an alkaline one due to the availability of one of our scale. So just to put that in perspective, our electrolyser is 224 kilowatts, whereas now you're looking at 1 megawatt, indeed 10 megawatt type of electrolysers. So a lesson learned really is early engagement with these electrolyser suppliers and the market to ensure that that their program and lead times actually meet in with your own program. The other one, health and safety. I mean, this is first and foremost of all projects, especially when you're implementing on site and you have operational staff around it. So for us, minimizing the risk of an incident, whether minor or major, was key to the project. And the journey that we've taken in learning that has been huge. So early engagement with our colleagues and transferring the knowledge. So we had some knowledge transfer workshops early on, one on the health and safety of hydrogen, where we had our ERM gave to all the colleagues and all of the team involved in the project background into regulations and guidance on hydrogen, case studies as well of other projects where they've implemented hydrogen electrolysers. Also with the MABR, the interconnectivity of how we interface the electrolyser with the MABR system. So all of those early knowledge transfer workshops for us was key in terms of learning and understanding and mitigating any risk we may face later. On the back end of those knowledge workshops, it was key that we got early safety reviews of the process. So that included the internal safety review teams doing HAZOPs and bow tie analysis, but it also highlighted for us a gap in the specialist knowledge of hydrogen and implementing it on a water treatment site. So for that purpose, we then went ahead and engaged specialist process safety team and consultant to do independent safety reviews to ensure that the whole system, not just the electrolyser, but the integration with our end user hydrogen, the operational staff on site, but also the MABR safety team were involved. That leads us on to environmental. So obviously a risk to environmental compliance with any new innovation or demonstration plant on site was key. So an early decision there was to return any of the flows from the MABR or the drains back to the works, and then monitor it closely to negate any environmental impact. As with all projects, budget always a key risk. But with innovation, it's ever more so, because as you're learning and developing and working with your partners, you learn new things as you go that you're needed. So there was always the risk of an increase in capital costs due to unforeseen or unknown technical requirements. And these include electricity, civil, water, and all the power requirements that needed to run both of the projects. So again, mitigation, early engagement, if you can, with your suppliers. That included with MABR, but also our electrolyser supplier, who's Logan Energy. We also have been implementing the project over the last couple of years with unprecedented inflation, which has caused havoc with the budget, also with electrolyser, with the power requirements, and also in implementing a project on an operational site. So we have been lucky that we've got a great relationship with Ofwat, and we've had an inflation adjustment award to allow for those fluctuating market conditions. But we also took the initiative to implement a power management system, which allows us to operate the electrolyser at a lower turn down, so therefore drawing less electricity when the electricity tariffs are at their peak. So we've worked with the Anglian Water tariffs team and our suppliers to implement that to work for the benefit of the budget later on in the project. I mentioned before the procurement of the electrolyser of our size being available, but also the lead time. There are long lead times with electrolysers across the whole market. And I will mention here, it's not just the electrolyser. We were lucky to secure the electrolyser within 6 months. However, the components, such as the compressor, took slightly longer. And therefore, we are running slightly delayed on our programme by 4 months due to just the logistics of getting all the hydrogen components into the system. But being proactive, we ensured that we decoupled the MABR from the electrolyser unit. And as you can hear from Barry earlier, we've managed to have the MABR is up and running and commissioned. And we have oxygen MCPs on site to allow us to start to introduce the oxygen in case of any delay to the electrolyser, so it didn't prevent the startup of the trial. The other risk that we fancied is not that we had here, is not having a hydrogen end user available. So once we start the electrolyser and we start the hydrogen, the logistics of how we capture that and transport it off site for beneficial use required a lot of early engagement. We're in a unique situation in that we only have small quantities of hydrogen available, as we mentioned before, about 90 kilograms per day of hydrogen being available. So it's working with these hydrogen end users to ensure that we had somebody who could be available and could transport and utilise that hydrogen. They are element 2, and we went with them purely on the basis that they could offer a trailer, which offers us a week's storage, which minimises activities on site of changing in and out MCPs, which was the alternative. So early engagement would be a key lessons learned for us there with negotiating that kind of off-take arrangement. In terms of operating, it is a hydrogen plant and an MABR. The operational staff on site are much more familiar with operating the MABR in the sense that it has familiar technology such as some blowers and the instrumentation, and they are more familiar with that, so a bit more of an acceptance to operate that longer term. However, with the hydrogen, it is specialist operations and it needs specialist training. And so we took the initiative to have a maintenance contract by the electrolyser supplier for the duration of the trial, such that they will monitor it remotely. They'll address any alarms remotely if they can, or they will turn up to site to do any resets and obviously the maintenance that's required as needed, which is quarterly for the electrolyser unit. So they're sort of the key, I guess, key project risks and mitigations, but they are really our key lessons learned. And just moving on, we still have these. We haven't mitigated all of our risk, and as you can see, the health and safety will still be there, and we've still got to close out all of the safety reviews. We need training on site of the team, and there's the ongoing maintenance support as well. In terms of Anglian Water, it's new technology, so in terms of the approvals that is needed for safe operation and handover to the Anglian Water team, such as DESIR, the emergency response planning and the standard operating procedures, that all needs to be in place. So we need to collaborate with our partners, the documentation and the assurance that the plant can be operated safely with all these procedures in place. There's also the installation of the plant, and the At1 Alliance underneath Anglian Water provided the capital delivery partner for us, but there's also the CDM requirements, so principal designer, principal contractor for them. you know, a lot of interfacing, collaboration sessions and understanding of roles and responsibility needs to be talked about very early on in the project to ensure everybody's really clear on the roles and responsibilities for delivering such a complex innovation trial such as this. In terms of technical, hydrogen quality, now that is key because proving the hydrogen quality actually meets the ISO 14687 standard is there's only a few laboratories. In fact, I think there's only 1 or 2 across the UK currently that can actually test all of the components listed in that spec. And there's long lead times for those tests. So understanding that and having that in place obviously has been a learning for us. I mentioned before the hydrogen end user, having to work with them. If we have, as we've had a delay with the projects, it's ensuring that they've got the logistics in place, that when we are ready to go, and we hope we'll be ready to go in about 4 to 6 weeks, that the trailer is in place and ready. And then I think I mentioned before about the maintenance plan. So that's the highlight of our key projects in risk. But what I want to say here quickly is what's gone well. Because we are on site, as Barry mentioned, with Oxymem. You can see there the picture. So how have we done? Well, it's been a really good team. We've mobilised with good pace and energy over the last couple of years. We've got a great collaborative relationship with all of our partners, which has really stood us in good stead for innovation. And it's key to delivering innovation projects, I would say. I mentioned we've got great feedback with Ofwat. And overall, from all of the universities and our water colleagues, it's been open and collaborative from the word go. So we've been lucky in that sense and key. Julia mentioned about the project objectives. We haven't changed those from when we started. And those early knowledge share sessions were definitely beneficial for the design teams. I mentioned before early engagement. That's gone well for us with those early conversations to make sure things were in place. Hydrogen technology, I mean, we are gathering pace. We've still got a hydrogen technology gap, I believe, internally and externally, we're finding, but the skills are developing and we are learning. And we are learning about the regulations needed, particularly to have a hydrogen plant on a water treatment plant. The MABR is up and running, as Barry said, and we will, over the next 6 months, we'll get more data and be able to share those insights with ourselves. As such, with all the work that Cranfield have just mentioned with the final effluent and DRM in helping us to develop that hydrogen strategy later on. And overall, I think, you know, we've been lucky that we've got a flexible collaborative approach across the whole of our partners, Anglian Water and Jacobs, in terms of a collaborative approach. A few things, just recapping what could have gone better. Complex, we've got 12 partners, so there's been a lot of complex contractual arrangements for innovation for the 12 partners, some with proprietary equipment, so there's some IP protection, but trying to negotiate the same contract for all 12 partners was rather tricky, but we did manage it. Of course, putting anything on a brownfield site, as I mentioned, our capital delivery partner, earlier engagement with them would have been beneficial. But it's a bit like a chicken and egg. It was hard to engage them early because we didn't know what we were building on site until we'd engaged the others. So I think bringing everybody together as early as possible is certainly a key learning. And understanding roles and responsibilities throughout the project is also key in terms of health and safety, CDM, operational interfaces, and all of that goes with the innovation. And I think the only other one here is what could have gone better is complex interfaces between all the package equipment. As I mentioned, we've got Oxymem, we've got Logan, and we've got Element 2. And we also had it being delivered by Capital Delivery at One Alliance on a working site. So all of those interfaces needed to be discussed at length and understood very early on, such as the oxygen pipe work that's coming over from Logan into the Oxymem, the shut-off requirements and the safety systems, then how they need to speak to each other. All of those were learnings. And I would just say it's just working together, collaborating, and keeping that communication going at all ends. And I think I've covered most of these here in terms of the technical insights that we've gained to date. I think the key one really is about the hydrogen technology experience resources. That is one thing that we are finding with the hydrogen, that there is a lag in the technology, a lag in the capability and competency of teams, and it's lagging behind the pace of development, such that a lot of the people move on. It's quite transitional. They're moving on quite quickly to other opportunities that come by. So that is one learning that we've had. And I think that brings me, I think I've covered most of these in other slides, or my colleagues have. So I think that brings me to the end of my session. And I guess it goes back to you, Leah.
Thanks so much, Lisa, and thank you to everybody who has presented so far. I think it's been a really great presentation, and we've had lots of really great questions coming in through the chat. So we are just going to go to a quick 5-minute break before coming back for our Q&A session, and then we'll close up at about 12 p.m. So as I say, we've got the Q&A session coming up, so please do keep putting your questions in the chat and we'll look to answer them in there. So the time's now 11:28. And we're going to go to a quick 5-minute break, returning at 11:33. Thanks, everyone. Hi, everyone. So we should just be returning back for the Q&A session. I'll give our presenters a minute just to come back and get their cameras on and whatnot before asking the first question. I'm also just going to stop sharing the presentation for now, just so we can see our lovely presenters a little bit better. Hello. Okay, so first question, I think, is for Barry from Claire, who wanted to know, is there verified evidence that MABR is reducing nitrous oxide emissions? Oh, I don't think Barry's, there he is.
Yeah, so I kind of say, as I said in the presentation, yes and no and maybe. So I know of a plant in Canada where they've installed MABRs as an upgrade. It was a plant that had only aeration tanks beforehand, and it had a sludge age of about 7 days. So in the wintertime, they only had partial nitrification. So they ultimately built a new anoxic tank where they installed the MABR. And there was a provisional study that said that the nitrous oxide emissions were reduced by 90% after the install of the MABR. But it was quite a unique situation because the plant was operating on the edge, which in terms it wasn't fully nitrifying, which is known to increase the likelihood of nitrous oxide emissions. And then, of course, they added in an anoxic tank, and the MABR modules were removing between 30 and 60% of the ammonia, which is quite a lot for a drop-in situation. So the MABR basically took out the peak loads of ammonia. It meant that the aeration system downstream had to do a lot less of the nitrification, so they got much better effluent ammonia concentration. It was no longer operating on the edge. It also allowed them to reduce the aeration supply to the fine bubbly fusers by 50%, and that significantly decreases the amount of nitrous oxide that's stripped. So in that case, it had a massive impact. But you don't find too many plants that are operating like that. I know of a plant that's operating as a pure biofilm system as a tertiary treatment. So there's basically only ammonia, not any COD, and you need to be really careful how you operate that plant. Otherwise, there can be really high nitrous oxide emissions because there's no COD available to do the denitrification. So I'll finish where I started. Yes, no, and maybe. It all depends on the operating conditions of the existing plant. But there is evidence that it can reduce it in specific circumstances for sure.
Fabulous, thank you. And I think you've just got a couple more questions for yourself, Barry. So moving on to one from Duncan. Does the MABR use oxygen or air as the gas to be injected into the activated sludge?
Yeah, typically in the activated sludge, we're using air. Ideally, I would like to use air coming from the existing blowers. It would just make it simpler. Most of the plants we've done so far, we've added in new blowers. That was more a contractual thing. It kept everything nice and clean to have one new system. We haven't used oxygen because sometimes we typically install in an anoxic zone, so we don't really want to oversupply air either. Otherwise, we could potentially have a negative impact on the denitrification in there. That said, I mean, maybe if we use pure oxygen, get a better concentration gradient of oxygen between the aluminum and between the bulk liquid. Maybe we could use a lot less MABR modules if we use pure air. That would be a cap CapEx advantage, it would also result in less carbon emissions because we need less MABR modules, so less steel, less silicone, less carbon, less embedded carbon. But we haven't really looked into that. As I said, this is only the second trial we've done with pure oxygen, and it's focusing on a pure biofilm system where there isn't any activated sludge.
Thank you so much. And just another one from Duncan for you, which I think you partially answered in your presentation, but just in case you wanted to add anything else. What is the material of the MABR membranes, the carbon footprint of manufacture and lifetime?
Yeah, so the materials in our membrane is made from PDMS, so silicone. We also have some PVC headers and we have stainless steel supports. The expected lifetime is 20 years. That said, our standard warranty is 1 year. Any other warranties outside of that, we deal with on a case-by-case basis. We have plants that have been operating for up to 8 years with our membranes, and we don't see any significant deterioration, just some slight changes in the tensile strength and elongation. But yeah, we think they can last at least 20 years. As I said in the presentation, they're poreless, so there's no pores that are going to clog. The biofilm is our friend, so we just need to scour the biofilm to take it off, but we're not using chemicals which typically damage UF and oral membranes. In terms of the carbon footprint, yeah, I think that I answered that kind of already. Typically in the UK, it would be a 4-year payback in terms of energy savings. It really depends on the electricity mix that you have. It depends on the operating condition of the plant. So for me to tell you that there's a certain amount of emissions per module, it's not going to help. So anyone who wants more information can contact me directly.
Perfect. Thanks so much, Barry. So Connor, one for you from Tom. Again, I think you've partially addressed it in your presentation, but just in case you wanted to reiterate anything, he asked, do you expect the power used to preheat FE so that it is suitable for electrolysis to be low enough that it is beneficial versus using potable water?
Yes, so I think from my understanding, it's the energy requirement to treat, I guess, wastewater or final effluent. It's always worth doing that pre-treatment process before going into the electrolysis process, in terms of if you were to do your electrolysis on a lower quality feed, you're actually wasting energy then in your electrolysis process, which is going to ultimately, you'll be wasting more energy doing that. So I think the initial pre-treatment upfront is always worth investing in ensuring that you get the highest quality feed for your electrolysis process. I see Luca hopefully nodding in agreement.
Perfect.
Just to add to that as well, Connor, I guess from a purely from a water availability perspective as well, it's not necessarily just an economic challenge. It's a water availability challenge in certain areas. So, you know, regardless of whether we utilize final effluent for potable demand or for energy demand via electrolysis, I guess there's more barriers from a potentially for a potable use of final effluent. So it's an availability thing rather than just purely a carbon footprint or carbon driver.
Fabulous. Thank you, Michael. So another one for Barry from Duncan is, what is an approximate footprint saving using MABR versus conventional AST? Does the MABR operate at a higher MLSS?
So there's two parts there. So obviously if you have an existing asset and we can drop into the module, I mean, it's an infinite saving because you have zero tank requirement versus another plant that needs an activated sludge, which you need new tanks. For greenfields, yeah, I mean, that's harder to answer. Depends if it'll be a pure biofilm system or it'll be an IFAS biofilm system. If it's an IFAS biofilm system, then we need to work with the end users to agree kind of new design standards for an MABR in terms of the size of your activated sludge. But I guess you can easily save 20% of the volume for a greenfield IFAS type MABR versus an activated sludge, and then probably more than that as well. What was the last part of that question?
He asked, does the MABR operate at a higher MLSS?
That little bit trickier. So in terms of in an IFAS configuration, the MLSS concentration is determined by the downstream settlers. So we'll have to operate at what concentration we get. When we're in a pure biofilm system, I mean, we don't have any MLSS really. All the bacteria are attached onto the membrane. Roughly speaking, if you were to take all of the biomass off our membrane and resuspend it in the volume of the module, then we would have MLSS concentrations between 11 and 16 grams per liter. So that's significantly higher than active late systems, but that's not really the point. I mean, we're selecting for nitrifying bacteria close to our membrane, so we're up concentrating the bacteria that get washed out really quickly. So not really something to compare to. It's really the abundance of nitrifiers in there that's much more important. But yes, we have high biomass concentrations.
Perfect. Thanks, Barry. So a final one for you, Barry, from Duncan. Do you need a frame to be installed in tanks in order to drop in cassettes?
That depends. So in the images I showed there, yes, there was a frame installed in the tank. In that particular site, the tanks were, I think, 40 years old. And the decision was made that they didn't want to add any additional loads to them. So then there was a frame was installed. In most of the other plants that we are installing them in, we will support the modules from the existing structures. The module itself it weighs 700 kilos when it's new, but actually, because of the air inside the membrane and the silicone, the net weight when it's the net gravitational force is only about 150 kilos. So there isn't really a lot of weight on those walls as long as there's water in the tanks. So it really will depend on case-by-case basis and what's the quality of the existing tank structures, but we would prefer to use the existing walls if we could help it.
Fabulous, thank you. And then one for you, Luca, from Claire, who has asked, is there any work looking at extracting ammonia from wastewater and then using it as a hydrogen source? I think we've answered this partially in the chat, but if you wanted to add anything, Luca, there we go.
Yeah. So I think the answer is yes. I think the focus of the TRIP carbon reduction project is on electrolysis to produce hydrogen using final effluent. I think that the message was clear for today, but it's not the only way that potentially the water industry has to produce or recover hydrogen. So ammonia is one. So of course the water industry spend billions or millions. I don't know if they get billions to get rid of ammonia, but actually ammonia is a source of hydrogen, can be recovered and transformed into hydrogen. And yeah, my colleague Ewan McAdam is active on these. I think they typed in the chat that there is a not funded project looking at that. So it's probably going to be a spring event soon on that. I think this flags also the kind of unique position that the water industry is in, because if you put a list of sources of hydrogen, basically the water industry ticks a lot of boxes. We mentioned water for electrolysis. The water industry deals with water. We mentioned ammonia. They got plenty of ammonia that potentially they can recover. Gasification, they have sludge they need to get rid of. Methane reforming, well, they produce biogas from where biomethane is recovered and potentially can be converted to hydrogen. So really the industry is in an interesting position to meet a variety of demand and offer a variety of ways to produce hydrogen. And yeah, I think Triple Carbon Reduction Project is an example of that. It's not the only one.
Perfect. Thanks so much, Luca. And then the next question is for Connor from Ryan, who wants to know what options have been investigated around the market uses of products of demineralization?
I think, to be honest, I'm not 100% sure on this one in terms of products for demineralization. So I might have to get back to you on that one. Sorry.
No, you're absolutely fine. Don't worry. We can move on to.
Lee, is there a way we can check what's meant exactly by that question in terms of whether there was specific, was it resource recovery type things or what was meant?
Yes, so we can't have the audience speak, but Ryan, if you want to just kind of clarify what you meant in the chat, I can ask the question in a second once you've popped it in the chat for us.
Cheers.
So while we wait for Ryan to do that, he's also got another question for Lisa, and he wanted to know who are the end users and which were investigated/approached.
Yeah, so the hydrogen end users for our project is a company called Element 2. We actually went through a process where we reached out to about 8 or so known hydrogen end users, such as I think Octopus, Element 2, Geopura, Rise, I think springs to mind. So they are sort of other end users. So it was really down to what they could offer us and a collaborative, what we offered them and what they could offer us. Because of our small quantities of hydrogen that we produce, it meant that some of the larger people like Octopus weren't actually, it didn't make viable sense for them to support this particular project just because our quantities were so small. Whereas Element 2 were keen to capture or store the hydrogen for us in a trailer, which gave us the advantage. We have then one trailer on site that needs to be changed on a weekly basis, which then minimised the amount of movement of trailers and trucks on an existing site. So that offered us that advantage. And their end use is actually currently planned for a well-known car test facility for hydrogen. So it has a green circular use.
Fabulous.
Yeah.
Thanks so much. So Ryan's just clarified that he did mean in terms of resource recovery for his question. So Connor, I don't know if you'd like to pick that up now. Do you want me to repeat the question at all?
Yes, please. Sorry. Thank you.
No, you're fine. Don't worry. So he put, what options have been investigated around the market for uses of products of demineralization in regards to resource recovery?
Yes, well, I think, Michael, I don't know if you've got anything on this, because I think it's probably not my area of expertise.
Yeah, and Luca, if you have anything to add as well, please jump in. But I guess effectively what we're getting is a concentrated wastewater stream or an equivalent to the final effluent that is more concentrated. So the economics of recovery will potentially be, multiplied. So there is it sort of makes everything that is already in sort of we're investigating a little bit more possible, I suppose, or a little bit more feasible because there's a concentrated stream available. So fundamentally, it's the same type of things that we would look to recover, but they might just be in higher concentrations and slightly lower volumes that make it more manageable. It hasn't been a part of this project to specifically look at that, but it's a wider sort of area of interest, definitely, that we're looking at both across effluent reuse, but also across desalination, sort of brine waste streams. And our own nitrate plant and different things that we're operating currently as well.
Perfect, thank you, Michael.
Yeah, and if I can just add, I think Michael kind of explained. I think there's an opportunity here for the water industry again to look at those synergies. Does it make sense for them to produce relatively small volumes of high purity water for either internal electrolyzer or to supply water to a number of external takers? Probably yes, probably not. It's for them to decide the case, but there's also an opportunity here to look at a more to meet a wider demand of water and have a plant that can produce water for hydrogen, but also water for other uses. We mentioned industry, we mentioned agriculture. It can be down to potable. So is exploring that variety of options that the industry have to meet that demand. And even on the relatively small water demand, that actually you can play the unit to have a relatively small water through, and so very small brine volume generation. So if maybe management of the brine is a concern, so you can go for a very small recovery and have everything left pumped back into the final effluent. So there are a variety of options that can be considered.
Perfect, thank you, Luca. Did anybody else have any thoughts on that one at all they wanted to add, or no? Perfect. So just some questions that have come directly to us, not in the chat. So first up is, how big a challenge are N2O emissions for existing plants, and can the Maybar help?
Yeah, so that kind of goes a little bit back to the question: is there any proof that the MABR can reduce nitrous oxide emissions? And I still think there's quite a lot of work to be done to understand what are the nitrous oxide emissions from different plants. There's been a lot of reports out over a lot of years, but there's a huge variety in activated sludge plants, how they're designed and how they're operated. So I think nitrous oxide is a really big issue, but quantifying it well, I don't think it has been done yet. So that would be the first step to understand what the real issue is today, and there's quite a bit of work to be done on that still, I think.
Perfect. Thanks,
Maybe
Barry.
Michael or Julia may have something to add on that one. No.
No, perfect. Okay, so does it make sense to replace fine bubble diffusers with MABR modules?
Yeah, in a word, no, at least not financially. So maybe from nitrous oxide emissions and energy point of view, yes, but we've had that question a lot when we started off. So can we take out all our fine bubble diffusers? But unfortunately, the payback time for installing the MABR modules, it just isn't there. It's in the order of 30 plus years. So from a financial point of view, it wouldn't really make sense. So the MABR really is seen as, we see it at the minute as it's when the existing plants that have some sort of need to expand for whatever reason is better effluent quality requirements or more flow, more load, then that can be a more applicable place for the MABR.
Perfect, thank you. So what else might there be in terms of benefits of co-location and electrolysis within the water industry or other industries? No thoughts on that one?
I'm happy to say a few things if yeah, so I think well, in terms of co-location of electrolysis with other industry, I think as well, I briefly mentioned it on potentially to utilize waste feedstock streams for the production of hydrogen. It's obviously obvious key benefit, but then I guess you've also got in terms of the electrolysis production producing oxygen, potential uses for that. So I guess existing demand, I guess for oxygen could be from for medical grade oxygen, but equally you could have oxygen used in other decarbonisation processes. So some industrials may be looking to decarbonise via oxy-fuel combustion as a potential route. I know, well, other industries, not in the UK so much, but for blast oxygen furnaces, that's, I guess, a non-UK specific one, but also for other forms of hydrogen production that might use, so typically blue hydrogen production, where an autothermal reforming process might require an air separation unit, which produces oxygen. You can, I guess, use some of that offtake oxygen to feed other hydrogen production processes as well. So I think, yeah, co-location, there are lots of synergies to be explored that I think there are lots of future opportunities to investigate in that area as well.
Perfect, thanks, Connor. And then a question from Christian. How does reject water from electrolyzers affect the main wastewater treatment plant? Is there a need for a side stream treatment for the rejected water?
Yeah, I've typed an answer quickly. Sorry, there's might be a few typos in there.
Oh, you're fine.
I think it will depend from the scale, of course, of the water treatment. So if we use the example I presented, so the amount of the electrolyzer needed, it was 0.5% of the dry weather flow. So probably the reject can be pumped back in the head of the work. So there's probably a little need for further treatment. And again, it does depend from the how to say the recovery rate of the water. So if you go for a relatively low recovery rate, you're not going to concentrate the pollutants in a very small stream. So it can probably pump back in the head of the work or stay with the final effluent. I don't know if Michael has any comment. For larger plants, maybe the picture is different.
Yes, so I guess it's exactly that. It's the percentage of the flow that we're considering. But I guess also when we are introducing it, effectively we treat it in a similar way to it's like a trade effluent or any other sort of concentrated load into the head of a work. So we might be able to manage some sort of buffering capacity for that, be it sort of that it would be proportionally put in with the flow or different things. So we would manage it around weather events or different sort of other loadings and things that the works would be experiencing. But typically it would be a very low percentage of the design capacity for the works. And if it's not the case, it could be exported to a different works as well, although it's probably best to keep it, just due to the nature of the characteristics of it, keep it to the works that it was designed for, that it originated from.
Perfect, thank you. And then a final question, I think probably for the Anglian Water team. How is the project being viewed by developers who are considering hydrogen production projects in the near future? Is the planning approval of hydrogen production facilities taking water into account?
So I don't know if Connor, you have anything to add to this, but I guess yeah, I mean, what we're sort of finding is that we're getting a lot more contacts from different developers. We're being engaged a lot more because of that water, the significance of water in the planning processes, which is very welcome from our perspective. And the sort of the Environment Agency and different bodies that are part of this are showing a lot more interest and giving it a lot more time and resource recently. Yeah.
Yeah, I think just to add to that, I think from what engaging with project developers, I think they're increasingly realizing that water is likely to be a constraint, and there's going to be a lot of competition to secure a sustainable water supply. I think there's going to be a lot less water available, and a lot of demand for it is, I guess, the summary. And so where it's not, well, it's very unlikely that they're going to be able to get it from the environment. These project developers are having to get a bit creative with where they're going to get that water from. So I think utilizing waste streams and from existing sources is going to become increasingly important moving forward.
Perfect, thanks Connor. Okay, so I think that wraps up today's showcase. So I just wanted to say thank you to everybody in the audience who's taken time out of their day to join us today. We do hope you found it a valuable session. Thank you also to the team from Anglian Water and all the partners too for sharing the project learnings so openly with us today. Lots of really great information, I think, in that presentation. I believe my colleague Kira has just popped a poll in the chat about today's session. So if everybody who's come today could please just take a moment to give us some feedback, we do find it extremely valuable. We'll also be posting the recording of today's showcase on our platform, along with the written case study shortly, which should hopefully be available within the next week. Any questions that haven't been answered during today's event will also be uploaded alongside those too, but I do believe we've answered all the questions in today's Q&A, so that's great. So thanks again for everyone for coming, and have a lovely rest of your day. Bye.